Hello students, this again is your NOLA Mathman coming to join you again to do another math lesson that may be giving people trouble. And so unlike Superman, I cannot leap tall buildings in a single bound. I'm not as fast as a speeding bullet. But in regards to math,
Superman got nothing on me.
after this video, students will be able to simplify complex numbers. The concept we're looking at is complex numbers. The skill we want to acquire by the end of the section of the video is we will learn how to simplify these complex numbers. So with no further ado, let's get started with our lesson. So we're looking at the concept of complex numbers. So what are complex numbers? They are simply numbers that are formed when you simplify negative square roots. Normally when you simplify square roots, they have to be positive because a number squared will always give you a positive number. But what happens when you have to interpret what we call a negative number? Well, this is when the concept of complex numbers were developed by mathematicians to deal with such situations. So there are two major principles regarding complex numbers that you have to know, and they will appear on the screen in a few seconds here. Here we go. First rule is I, the imaginary number, is equal to the square root of -1. And if you square I, which means you square both sides, I squared has to in turn equal -1. So we use this to simplify a lot of complex numbers in this section. You will be seeing these two rules utilized in great detail. So it's very important that you memorize these two formulas and be able to use them throughout the concept of complex numbers. Start with number one. So the square root of 99 is our first problem. Since it is not a perfect square, meaning there is no number squared that's equal to 99, the way you simplify a radical is you find a perfect square that is a factor of 99. Since 9 is a perfect square, and we know 9 goes into 99 11 times, we break the square root into 9 times 11. We take the square root of each of the factors, the square root of 9 and the square root of 11. So the square root of 9 is a perfect square. We put 3 times the square root of 11 will be our final answer of simplifying that expression. So we're done with our first problem. Radical. Radical is a fractional term. So we take the square root of 27 over 49. The first step of that is we take the square root of the numerator, 27, we take the square root of the denominator, 49, and we simplify. Since 49 is a perfect square, we put 7 there. Now we want to simplify 27. That's not a perfect square, so we have to break it into two factors, one of which is a perfect square, which is 9. So we break this into the square root of 9 times 3. We take the square root of each separate factor, 9 and 3. And then since the square root of 9 is 3, we will simplify that as 3 times the square root of 3. We put it back into the problem. And so the final answer will be 3 times the square root of 3 over 7. That simplifies number 2. So at this point, we want to let's see if we go to number 3 or 4. So now we're going to go to number 4, which is our first exploration of a radical that is a negative number. So we take the square root of -108, x to the 7th. And again, this is when we will use our first, illustration of the complex numbers being put into practice. So the first thing we want to do is we want to take the square root of -108 and take the square root of x to the 7th, and we break them into two separate radicals. So now we want to simplify -108 by writing -1 times 108, since we know square root of -1 will be I. And x to the 7th, we will write x to the 6th, which is the nearest even number under 7, because you always take the perfect squares, even exponents of perfect squares. So if you notice, that's a pattern there. And so we break x to the 7th into x to the 6th times x. We will now break that up into two what we will do now is we will simplify 108, and we got to find the highest perfect square that goes equal into 108. That will be 36 times 3. And so now we can take the square root of x to the 6th. We'll take the square root of x, which is the other factor. And now you just start simplifying the radicals. I is equal to the square root of -1. So in place of the square root of -1, we put I. The square root of 36, we want to rewrite that. We want to take the square root of 3, which are the two factors of 108. The square root of x to the 6th, and we have the square root of x. So at this point, we simplify all the radicals that we can simplify. Square root of 36 is 6. The square root of x to the 6th is x to the 3rd. The square root of 3 stays under the radical since you can't simplify that. And the square root of x stays under the radical. At this point, we multiply the terms outside of the radical, which are I, 6, and x to the 3rd, which will give us a product of 6i times x to the 3rd. And then we simplify the two terms under the radical, which will be 3 times x, and that will give us a final answer of 6i x to the 3rd times the square root of 3x. And so that is our simplified expression. So it seems a little complex, but the more you simplify complex numbers, the easier it'll become. So now we will go to a new set of problems here. We'll do number 5. So we will simplify the square root of -81x to the 6th power. So because we have two separate terms, -81 and x to the 6th power, we'll break this radical first into two separate radicals, the square root of -81 times the square root of x to the 6th power. So now we simplify those two separate radicals. Square root of -81 will be broken into -1 times 81, since we're dealing with a negative radical. We break that into -1 times. There we go. So the square root of x to the 6th is x to the 3rd, since again it's an even exponential value, so that's a perfect square. So now we will simplify the square root of -1, which is I, the square root of 81, that's a perfect square, which is 9. And so now we put all that together, and the answer will be 9i times x cubed, and that will be our final answer, 9i times x to the 3rd power. So we simplified number 5. So now we will go to our next problem here. Which one will we do next? Which one do you think we'll go to? We'll go to number 6. So now we have two negative numbers that are being multiplied, two negative radicals. The square root of -23 times the square root of -46. So what you first have to do, again, is rewrite the two negative radicals by the product of -1 times 23 in the first radical. And in the second radical, we will put -1 times 46. Now, once we do that, we will take the square root of each of the two products under the radical. We'll have the square root of -1 times the square root of 23. We'll have the square root of -1 times the square root of 46. Since we have the square root of -1, we know that is equal to I, so we write I for those two radicals that are the square root of -1. And we will have I times the square root of 3, let me say again, I times the square root of 23 times I times the square root of 46. So at this point, we can multiply the two i's together, and that will give us I times I, which is equal to I squared, we will find out. And then we can take the square root of 23 times the square root of 46, multiply the two products, and make one big radical. 23 times 46 is equal to 23 times 23 times 2, because 46 is 23 times 2. And that gives us a perfect square, because the square root of 23 times 23 is simply equal to 23 to the second power times the square root of 2. Square root of 23 squared is obviously equal to 23. So I squared, we simplify, is -1. The square root of 23 squared is 23. And we multiply that by the square root of 2. And so our final answer will be equal to -23 times the square root of 2. There we go. So we have simplified number 6. So now let's do number 7. We have 3i times -2i times 5i. And so we will multiply these three imaginary numbers and create a product. So according to the principles of multiplication, we will multiply the like terms together. 3 times -2 times 5 are our integer values, and we will multiply I times I times I, which are like terms. So 3 times -2 is equal to -6 times 5 is -30. I times I times I is I cubed, which is I to the third power. Or, since we know I cubed cannot be simplified, I squared is equal to -1, we write I cubed as I squared times I. We simplify I squared because we know that's equal to -1. I is by itself, and so we multiply -30 times -1. That will give us 30i. And so that is the final product for this problem. That's our final answer. So now we're going to pull up number 8. 8 is equal to, we want to simplify I to the 11th power. So again, we want we want I squared, so we know that if you want to simplify I to the 11th as I squared, you take I squared, you raise it to the 5th power, which is I to the 10th, and you multiply by I. Since -1 is equal to I squared, we substitute that in. -1 to the 5th power is -1. -1 times I will give us a final answer of -I for this problem. So now we're going to do problems 9 through 12 here. We'll start with number 9. We're going to simplify I to the 65th power. So again, we want to represent i's in terms of I squared because we know I squared is equal to -1. So what factor can we multiply I squared to get close to 65? That would be I squared to the 32nd power, which is 64. Since we have an I left over, we multiply by I. We substitute -1 for I squared. That will give us -1 to the 32 power. Since it's -1 to even power, we know it's +1. 1 times I is equal to I. So the final answer for this problem is I. So now we'll go to number 10. So in number 10, we have our first illustration of adding what we call complex numbers in the form of A plus BI. So A represents the whole number and BI represents the imaginary number. So when you add these two type of numbers, you actually treat them like terms. So what I do is I line them up vertically. We have 7 minus 8i, we have -12 minus 4i, and that will give us an answer of -5 minus 12i. We simplify them together. So again, you want to line up the like terms when you have the two complex numbers. 12, we'll do a subtraction problem. We have 10 minus 4i minus 7 plus 3i. So we want to do, subtraction is adding negative numbers, so we want to distribute -1 into the last two terms. So -1 times 7 will give us -7, which you're seeing the work here, and we will distribute -1 times 3i. Now once we do that, we will add the product, the sum of that to 10 minus 4i. So that will equal -7. And -1 times 3i is -3i. At this point, we have an addition problem, so we can line them up vertically like we did in the last problem. We put -7 under 10, we put -3i to -4i. 10 minus 7 is 3, negative 4i minus 3i is negative 7i, and you get your final answer. Very good. So now we've done a problem where we've added complex numbers in the form of a plus bi, and we've subtracted two complex numbers. So in this concept, we're not only adding and subtracting, which we did in the last group, now we're going to be multiplying these complex numbers in the form of a plus bi. The first problem we want to do is multiply 7 minus 6i times 2 minus 3i. So what we want to do with this is we want to use the same process we use for multiplying polynomials, which is the box method. So we create and treat 7 as a separate term and negative 6i. And we use a length to represent those two, and we use 2 as a length and negative 3i. We create the four products. 2 times 7 is 14, 2 times negative 6i is negative 12i, 7 times negative 3i is negative 21i, negative 3i times negative 6i is 18i squared. So now we write that out and we simplify those sums. So we have negative 12i and negative 21i, they're like terms. We put 18i squared, since we know I squared is equal to negative 1, we will substitute negative 1 for 18, as you will see in a sec. Since the I terms are like terms, we simplify negative 12i, negative 21i, they're equal to negative 33i. And then we will multiply 18 times negative 1, giving us negative 18. We simplify the like term, 14 minus 18 is negative 4. And we write negative 4 minus 33i, which is our final answer. Very good. So it's a lot of work. Hopefully you got that down in your notebook so that you can use them to solve product problems like number 14, which you would use the same process that we just did number 13. You would use that same process in 14. So now we're going to do to a fractional imaginary root problem, a complex number, where we will have to what we call rationalize the denominator. So what we do is, in order to get rid of 4 plus 2i, you multiply by what we call its complex conjugate, which is 4 minus 2i. And so we multiply the top, the numerator, 3i times 4 minus 2i. You distribute 3i into the grouping symbol, creating two products, 3i times 4 and 3i times negative 2. 3i times 4 is 12i. 3i times negative 2i is negative 6i squared. We substitute negative 1 for I squared, which would give us negative 6 times negative 1, which is positive 6. And so your final answer will be 6 plus 12i. That is the final simplification of 3i times 4 minus 2i. So in the numerator, we can now write 6 plus 12i. So at this point, we will simplify the denominator by multiplying the products of 4 plus 2i and 4 minus 2i. And since they're two-term expressions, what we call, it's almost like multiplying two binomials or two polynomials, we will use the box method again as we normally do. So each of the terms will be a separate length. We will have 4 is one length. We will have positive 2i. The other length vertically will be 4 minus 2i, and we get our four products. 4 times 4 is 16. 4 times 2i is 8i. 4 times negative 2i is negative 8i. And negative 2i times 2i is negative 4i squared. 8i and negative 8i cancel out, so we have 16 minus 4i squared. We substitute negative 1 for I squared. That gives us a product of negative 4 times negative 1. That will be 16 plus 4, and so the final answer is 20. And so we put that in the denominator. And so our final answer will be 6 plus 12i over 20. We can simplify that by breaking the complex number into two separate fractions, which are 6 over 20 plus 12 over 20i. So now we will reduce the two fractions, and our final answer will be 3 over 10 plus 3 over 5i. And so that's your final answer for number 16. Very good. So at this point, we have covered quite a few different types of complex number problems. We're going to do another kind where we will solve. So now we're not simplifying, we're going to actually solve each of the equations here. So we'll bring up these problems here. So we're going to put up number 18 and we're going to simplify that. That problem reads 5x squared plus 125 equals 0. So you solve for x squared like you solve it for x, and then you take the square root of both sides. So in order to do that, the first thing we have to do is get rid of 125. We subtract both sides by 125. That gives us 5x squared equals negative 125. To get rid of the 5, we divide both sides by 5. Because it's 5 times x squared, the inverse of division. We take the square root of both sides to get x. Square root of x squared is x. The square root of negative 25 will be plus or minus. The square root, since it's a negative exponent, we have to break it into negative 1 times 25. You know the square root of negative 1 is I. The square root of 25 is 5. And so the answer is x equals plus or minus 5i. Go for that. Next one we want to do is number 22. We have 8x squared plus 96 equals 0. So again, we solve for x squared like we're solving for x. We got to get rid of positive 96, so we subtract 96 from both sides. At this point, we have to get rid of 8, the inverse of multiplication division. We divide both sides by 8. We get x squared equals negative 96 over 8, which is negative 12. Take the square root of both sides. We will get x equals plus or minus the square root of negative 12. We know since it's negative, we have to have the product of negative 1. 12 is not a perfect square, so 4 is a factor that is a perfect square. So we say 4 times 3. Square root of 4 is 2. The square root of negative 1 is I. We take those out of the radical, and so x is equal to plus or minus 2i times square root of 3. And so what you do to simplify and solve this for L and M is you have to set each of the separate terms equal to one another on the left and the right side of the equal sign. You'll see what I'm saying in a sec. So we'll do number 26. We have 3 minus m plus 7l minus 14i equals 1 plus 7i. So what we want to do is put the like type terms together. So what we do is we want to classify 3 minus m as an a term because it doesn't have I, and 1 does not have I, so we make those two terms like. And the two I terms, which are 7l minus 14 and 7i, we label those two to put those two together. So that's what we do. So once we label them, we put the 1s together, we put the 2s together, we solve for m by solving the 1s. So in other words, 3 minus m equals 1. We subtract 3 from both sides. We divide by 1, and m is equal to positive 2. To solve for L, the second equation, we add 14 to both sides using the inverse operation. Using the inverse operation, we divide both sides by 7, and L is equal to 3. And so we have now solved for M in 2. And so with this concludes our lesson on complex numbers. Now you'll be able to simplify complex numbers or negative square roots. And until we meet again, this is NOLA Man signing off. Until we do another math adventure, have a beautiful day. Bye-bye.